In this video, we're going to explore digital discrete time all-pass filters. We're going to be looking at what they are, why they're useful, for instance, using them to generate other filter types or implementing digital reverb algorithms. Then we'll go through the theory of first and second order low-pass filters, how to implement them in C code on an STM32 microcontroller that will then finally run on this digital guitar effects processing platform we've seen a couple times previously on this channel. Once we've gone through the theory and implemented this on this STM32 processor and got audio running in and out of the system, we'll perform actual frequency response measurements, looking at the magnitude and phase characteristics in real time and how we can adjust the parameters of all pass filters and what that means, both in the frequency domain and then also in the time domain, looking at the phase shifts versus frequency that these all pass filters introduce and how it can affect their behavior. Overall, then, this will be a building block for future videos where we'll be implementing digital reverb algorithms, which I think personally is very cool, but we need to cover all pass filters before we can do that. Before we continue with this video, I'd strongly suggest checking out my DSP playlist where we've covered many different types of IR filters, FIR filters, and general signal processing techniques, and also how to implement them in real time on a microcontroller-based system. I'll leave a link to this playlist in the description box below, and I'd strongly suggest checking a few of those videos before we continue with this one, specifically the Z-transform and IIR filter theory and implementation video. A huge thank you to JLCPCB for sponsoring this video. I had these guitar DSP PCBs manufactured and assembled by JLCPCB, and they did an absolutely fantastic job. JLCPCB is super easy to use, affordable, and reliable. In terms of ordering, all we have to do is go to jlcpcb.com, click on Instant Quote, upload your Gerber files. It'll automatically detect the core parameters such as layer count, dimensions. Then you can choose whatever parameters you want for your PCB, such as PCB color, surface finish, and much more. If you want assembly as well, you can simply tick PCB assembly, upload your bill of materials and component placement files, and that's pretty much it. So super easy, but also super affordable. For example, for 5 PCBs, 50 by 50 millimeters, 6 layers, it's only $2 and includes V and pad, so epoxy filled and capped vias, along with unique surface finish. And also at the time of making this video, this is also true 8-layer PCBs, just $2 for 50 by 50, 5 pieces. So super affordable, super easy, but also very reliable. I've had a great experience using JLCPCB for nearly 10 years, and it makes prototyping, developing much simpler. So I'd strongly suggest giving JLCPCB a try, and I'll have some links for those in the description box below. Before we move over to implementation and testing, we of course have to go through the all-pass filter basics, look a bit of a theory, and then we use that theory to implement these all-pass filters in C code running on an STM32 microcontroller. If you haven't heard of all-pass filters before, they might sound a bit weird. That is because all-pass filters actually don't alter the magnitude characteristic when passing in an input signal and getting an output signal. The amplitude of that signal at steady state is unchanged. This is different to filters we typically see, such as low pass or high pass or other types of filters. What happens with all pass filters is that the magnitude is unchanged, but we are changing the phase response of the signal at the output. That means if we, for instance, pass in a sine wave of a certain amplitude, A, with a certain nominal frequency, omega, passing that through an all-pass filter, we still get the same amplitude sine wave out, still at the same frequency, but with a phase shift that is dependent on that frequency. That also tells us about the name all-pass filter, where that comes from, is because all the magnitudes are passed equally at 0 dB, 1x, 1 times gain, but there's an typically increased phase delay with frequency, and we can see that on the right-hand side on these graphs. On the x-axis, we have the normalized frequency. On the y-axis on the top graph, we have the magnitude in dB, and that's simply a flat line at 0 dB. However, the phase, which is the second graph below that, versus frequency changes. Close to DC, we have 0 degrees of phase shift, phase delay, but as we go up in frequency, we get more and more phase delay in the system. Below, for the sake of completeness, there's also a graph of group delay for, in this particular case, a first order all-pass filter, but we'll get into that a bit later on as well. Now, this does maybe seem rather bizarre, but this has a few use cases that are very important. For instance, all-pass filters can form and typically form the base building blocks for other types of filters, be that low-pass, high-pass, and band-pass and band-stop filters. They can be written as simple rearrangements or combinations of all-pass filters. In addition, all-pass filters are used for phase compensation, for instance, to minimize phase distortion in loudspeaker systems if you have a surround or stereo loudspeaker system in place and you want to correct the phase distortions due to differing placements and differing distances and phase delays to a receiver or to a listener. All-pass filters can also be used for channel equalization. If you want to correct specific phase shifts, you can do that with all-pass filters without affecting the magnitude response, at least at steady state. In this video, I would like to discuss first and second order IRR all-pass filters. That is, we'll go through the theory in a bit, we'll look at the C implementation on an STM32 microcontroller, run that on real-world hardware, and then examine the frequency and time domain performances with some very simple tests. The reason I like to bring up all-pass filters and that we should cover it is because very soon I'd like to make a video on reverberation or reverb algorithms, and some of these rely on all-pass filters, so we need to cover that in a basic video. Let's look into the first order all-pass filter, the simplest type of all-pass filter we can arrive at. And keep in mind, we will be in the discrete time domain. That's why we're only analyzing discrete time all-pass filters. They do, of course, exist in the continuous time analog domain as well. First order all-pass filter typically has the characteristic that we have a magnitude response that is flat at 0 dB of gain. We have one parameter we can adjust for first order all-pass filter, and that is the cutoff frequency. And at that specific frequency, in the phase response, we have a phase shift of minus 90 degrees. Then, as we go past that cutoff frequency, as the frequency increases, the filter phase response tends to minus 180 degrees phase shift in the limit. And we can see that quite clearly on the right-hand side. The magnitude response is a flat 0 dB. The phase response starts at 0. We go through a cutoff frequency where we arrive at minus 90 degrees. And then as we go up and up in frequency, up to the Nyquist limit, we then tend to minus 180 degrees of phase shift. The discrete time transfer function is shown here. We have a single zero and a single pole, and we have this one variable, or constant depending on how you implement this, C, which is related to the cutoff frequency using the equation on the right-hand side. So tan of pi times the cutoff frequency divided by the sampling frequency, Fs, minus 1, divided by tan of pi times the cutoff frequency divided by the sample frequency, plus 1. And this gives our coefficient C. Looking at this simple discrete time transfer function, we can see that we have one zero, which is located at minus 1 over C. Now, since C, given this equation, is bound between minus 1 and plus 1, 1 over C is going to be larger than 1, which means it's going to be outside of the unit circle, giving a non-minimum phase system. Non-minimum phase systems have a characteristic that if we apply an input signal or a step input signal, the step output actually moves in the opposite direction to the final steady state at the initial transient. Might be a bit difficult to see here, but I've applied a step input and actually the output goes negative before it recovers to go to positive steady state at 1. And that's very characteristic of non-minimum phase systems. Other than that single zero, we also have one pole which is located at minus C. And the pole, of course, has to do with stability, and that has to be within the unit circle, so the magnitude of that pole less than 1 if we want stability. And this is true if the cutoff frequency is less than Fs over 2, so less than the sample frequency over 2, which of course makes sense because that is our Nyquist limit. So therefore, this all-pass filter is stable, but it is a non-minimum phase system. If we go from our discrete time transfer function, we can very, very easily come up with our discrete time difference equation. So just taking the inverse Z transform, we arrive at this discrete time difference equation. So the current output sample y of n is our filter coefficient times our current input sample plus our previous input sample minus our filter coefficient times the previous filter output. And just as it reads here, this is exactly what we're going to implement in code later on. It's very, very easy to implement. All we have to do is pre-compute C, our coefficient C, and recompute this coefficient if we want to change our cutoff frequency on the fly. And again, we just use that formula with these tan terms in it. Other than that, we just have to store the previous input sample and previous output sample so we can compute the current output sample. And that's how easy it is to implement a first order all-pass IIR filter in discrete time in a digital domain. Moving on for that, another very useful type of all-pass filter is the second order all-pass filter, which builds on the first order all-pass filter. The characteristics are similar, where we have 0 dBs of gain in the magnitude, but at the cutoff frequency, we now have minus 180 degrees of phase shift because this is a second order system. And then after that cutoff frequency, beyond this, as the frequency increases, the phase shift tends to minus 360 degrees. Again, on the right-hand side, we can see that. So a flat 0 dB phase response and flat 0 dB magnitude response and a phase response that starts at 0 at DC, goes through the cutoff frequency where we have minus 180 degrees and then tends to minus 360 degrees as we go closer to the Nyquist limit. However, this is a second order all-pass filter, and other than the cutoff frequency, we do actually get another additional and adjustable bandwidth parameter. So we have a bandwidth frequency. If you look on the right-hand side of the phase response around this cutoff frequency, we can adjust the slope or the steepness or shallowness of this slope with this bandwidth parameter. So if we have a very large bandwidth, the slope is not going to be that sudden. If we have a very narrow bandwidth, we're going to have a very steep slope around that cutoff frequency. The discrete time transfer function is given here. I won't go through it terribly much, but we do now have two filter coefficients, C and D. Now, while C has the same form as before with these two tan terms, you need to note that we're not using the cutoff frequency, we're using the bandwidth parameter frequency. So FB instead of FC in this term. And for our new filter coefficient D, we're using this minus cosine term, where we're using the cutoff frequency in this term instead. So minus cosine 2 pi FC over Fs. On the bottom right-hand side, I've plotted a step response to one of these filters, and again, this is a non-minimum phase system, so initially I'm applying a positive going step, but the initial output transient actually goes opposite to that direction before it goes up and then settles at 1. So a non-minimum phase system. Going again from the discrete time transfer function, we can arrive at a discrete time difference equation, which is the equation given here. Again, we have two different filter coefficients, C and D, and we need to store more input and output terms because this is a higher order system. But we'll see how to implement that later on. All we're doing is pre-computing our coefficients and recomputing them on the fly if the cutoff and or bandwidth frequency changes, and we're storing previous inputs and outputs and then simply doing addition and multiplication. That's it. Now let's move over to the actual implementation. And what we'll do, as we saw at the start of this video, is implement this on an STM32 87 microcontroller-based guitar processing platform. I have a single mono input and a single mono output. I feed through some sort of analog filtering section into my ADC, which goes digitally then into my STM32 87, where we'll run the all-pass filter, feeds out to the DAC through analog filtering into the output. We've seen this system many times before on the channel, and I'll leave a DSP playlist in the links in the description box below so you can check out all the videos and also how to set up all the supporting code around this to run your DMA and I2S streams and so on. In terms of programming and implementation, the all-pass filter is super easy to implement. We saw previously we had these difference equations and ways of calculating the coefficients using the equations we saw in the slides, and then actually the implementation is very, very straightforward. We have to compute the coefficients, we have to store inputs and outputs, and multiply them together in a certain way to arrive at the output. A simple implementation of a linear discrete time difference equation. We'll quickly go over the implementation before we then look at some real-world measurements. Here I have my allpass.h header file. I'm using a struct to store the coefficients as well as previous inputs and previous outputs. And here I've just simply put in one struct that can be set to a first order type as well as a second order type. And then we have different calls to compute the coefficients if we want to use a first order or second order filter. We have an initialization function and a reset function, which pretty much just clears the inputs and outputs to 0. We have the coefficient set function, which computes the coefficients per the formula we saw previously. And then the update function, which takes a current input and provides then the output from the all-pass filter. Then in the .c file, the initialization and reset function simply just clear the coefficients and input and output buffers of our IIR all-pass filter. Our set first order coefficient function takes in our all-pass filter struct, the cutoff frequency we want in hertz, as well as the sample frequency in hertz. Now keep in mind, you always have to set your cutoff frequency below the Nyquist limit, so less than the sample frequency in hertz divided by 2, but this isn't implemented here just for the sake of simplicity. I'm pre-computing my tan term, which we saw in the equation previously, so pi times the cutoff frequency divided by the sample frequency, take the tan of that. And then our first coefficient, because we only have one coefficient, is that pre-computed tan term minus 1 divided by the pre-computed tan term plus 1. We only have one coefficient for the first order filter. For the second order filter, this is very, very similar. However, we now have another term, which is the bandwidth or the bandwidth frequency in hertz, in addition to the cutoff frequency and the sample frequency. We need to perform another pre-computation of the same term, except now we're not using the cutoff frequency in hertz, we're using the bandwidth frequency in hertz. Then our first coefficient is now tan pre-comp minus 1 divided by tan pre-comp plus 1, but keep in mind this tan pre-comp is different to that of the first order filter. Because this is a second order filter, second order all-pass, we need a second coefficient, and as we saw from the slides, that's minus cosine of 2 pi times the cutoff frequency divided by the sample frequency. And that's all there is to adjust in the coefficients, and you can use these coefficient calculating functions on the fly to adjust the all-pass filter in real time. Then what we of course need is the all-pass update function, which takes in our all-pass filter struct, takes in the current input sample we would like to process, and returns the all-pass output sample of our filter. Now, depending if you set up the all-pass filter as a first order or second order, we have two different equations. And again, this is just taken directly from the slides, directly from the difference equations we saw previously. For the first order filter, we take our output by multiplying the current input by our coefficient, adding to that the previous input, and subtracting from that the previous output times our coefficient again. For the second order all-pass filter, this is of course a bit more involved. We now have to do a couple more computations because we're concerned with the current input, the previous input, and the input before that, as well as the previous output and the output before that. And now we have two coefficients. It's a simple multiplication and addition of various terms, just taking the difference equation as before. Then, because we have memory, we have to shift that memory. So I'm shifting my inputs in time and I'm shifting my outputs in time. Now we can reuse these the next time this update function is called. And finally, I'm returning the current output of my all-pass filter. That's very, very simple and pretty much it. Of course, if you're just using a first order or second order filter and you don't want to switch them on the fly, you can get rid of this order term and just do one of these computations because this is more efficient. You don't always have to have this if statement in there. But this is just for demonstration purposes that we can switch between first and second order. Then in my main processing code, of course, we have to include the all-pass filter header file. We have to instantiate an all-pass filter struct to store our coefficients and input and output samples. And here I have some variable terms that we can adjust to change the bandwidth and cutoff frequency. In int main, I'm simply calling my all-pass filter init to clear the input and output buffers. And then for now, we'll start with a first order all-pass filter and move to the second order one, passing in the cutoff frequency and my sampling frequency. In my processing callback then, which is handled by the codec, driver, and the DMA stream, I'm looping through my input buffer. I have an additional switch on this board, so I can either output directly just the raw input signal, or I can output the processed all-pass filter output, which is just simply calling the IFX all-pass update function. The reason I've also put in an option here to output the unprocessed input sample is because that allows us to measure the delays and characteristics inherent in the system without any processing, because we need to calibrate that out to actually properly be able to measure our filter, but we'll see that in just a bit. But anyway, after the all-pass update has been called, we then pass that to our output DMA buffer. I have several potentiometers on the board and I'll map 1 and 2 of them to the all-pass filter cutoff frequencies as well as the bandwidth terms so we can play with these on the fly. So I'm just calling my all-pass set first order function as I'm changing one potentiometer, and I can do the same for the bandwidth, for instance, when I'm changing my second potentiometer. But that's pretty much it. So now let's upload this code to the board and actually measure these all-pass filters in real time and see if they match our theoretical expectations. For the gain and phase response measurements in the real world, we'll be using a Bode 100 vector network analyzer, but you could of course do this with any spectrum analyzer with a tracking generator, with an oscilloscope and a function generator. There are many ways of extracting the magnitude and phase response from systems. For this, I'm going to be using the Bode 100 because I can calibrate out the inherent delays caused by the processing platform itself, the filters, the analog filters before and after the ADC and DACs, just to make sure we can capture the raw, de-embedded phase and magnitude response of our digital filter, and I'll show you how to do that in just a second. In terms of connectivity, I'm going to be doing a transfer function measurement, so a gain phase measurement. We need to connect up the output of the Bode 100 to the input of this effects platform. Channel 1 of the Bode 100 will also connect then to the input of our digital guitar effects platform, and the channel 2 input will connect to the output of our guitar effects platform. And here, just a rough image of what's going on. I've got my Bode 100 output and Bode 100 channel 1 input connected to the input of my pedal, the Bode 100 channel 2 input connected to the output of the pedal. And this lets us then extract gain and phase information because we're measuring the input, we're measuring the output, and we're applying a stimulus to the input. And I'm programming the device using a Sega J-Link via CRY debug and a Tag Connect TC2030 programming header. Then moving over to the Bode Analyzer suite, what we want to do is set up a gain and phase measurement. And you can see the connectivity is also shown in this image, and that's exactly how we've connected up our system. So let's select that as our measurement. Now we have to set up our measurement. I'd like to do just an audio sweep. So I'm going to start from 20 Hertz up to about 20 kilohertz. I'm going to change my receiver bandwidth to 100 Hertz and keep the source levels and receiver attenuations as they are as default. Then we can also go to the top to transmission gain setup, and we can see I've kept this at 1-to-1 probes for the input and output channels. We can see we can't exceed more than 50 volts at the input of the Bode 100, and we can't exceed more than 3.3 volts at the output. So this is completely within range for the system that we're trying to measure. I've uploaded the first order all-pass filter code to the board, but for now I can use the foot switch, I can use a control on the pedal to feed the input directly to the output. So if everything's set up correctly, we should have a flat gain and phase response. If I just do a single measurement, and then I can go to View, Auto Axis Placement, 1 axis per chart, we can see because we're feeding the signal directly through, and we're around audio frequencies, so the cables don't really have terribly much of an effect, the gain is flat at 0 dB, so 1 times gain across our audio band, and our phase is also flat. And that's to be expected because this is just a straight cable through. However, if I now engage the pedal and currently my system is bypassed, meaning I'm simply setting the output to be the input, this lets us measure and see the transfer function nominally through the digital processing platform without any effects applied. So if I do another single measurement, we can see the magnitude response is of course different because now we're feeding it through the analog filters and through the whole digital processing system, and we can see that we have quite a bit of phase delay. If I on the right hand side click on unwrap phase, then right click auto optimize both axes, we can get a better idea of what is happening. The magnitude response at the top is the total magnitude response of the analog and digital hardware, no effects running, and the bottom is the phase response. And we can see as we go up in frequency, we really have quite a large phase delay. We can also on the right hand side change from phase to group delay, and we can see the overall delay versus frequency. And of course this isn't helpful if we're trying to actually measure what this filter is doing, because the effects of the filter might be dominated by the overall system response. So we just want to measure the response of the filter and de-embed the system. The way you can do that is calibrate with the pedal on, but with no effects being applied. So we want to characterize this system and null it based on this measurement. The way you can do that is go to User Range Calibration at the top, Perform New Calibration, and simply click on Through and Start. This will measure the system as it is now with no effects running, but we're capturing the entire effects chain, that is the analog and digital processing chain going on with no effects applied. Click Close, and this should now have de-embedded our system. So if I now do a single measurement again, we should get a flat magnitude and flat phase response because we've calibrated to this digital bypass signal. And we can see the scales have now auto-adjusted, but look on the left-hand side, on the y-axis, scale is very, very small, so it's milli-dB and milli-degrees of phase. So this is effectively flat. Now what I can do is engage the effect by hitting my second control button and actually causing effects enabled 2 to be on. That means we're passing our input straight into our all-pass filter, and the output is the output of the all-pass filter. So now we have the effect applied, but we've calibrated, we've de-embedded the system. I'm also monitoring a variable, APF, all-pass filter cutoff frequency hertz, that allows us to change the cutoff frequency on the fly using the first potentiometer of this system. So now I've set this to about 1 kilohertz, the cutoff frequency of my all-pass filter, and let's measure what this now does after calibration. Let's do a single measurement. And this is our measurement. Keep in mind, again, the magnitude is pretty much flat, although we see these excursions, but again, look on the left-hand scale, we're pretty much centered on 0 dB with only about 3 milli-dB excursions, so this is pretty much flat. So the magnitude is 0 dB flat, exactly what we expected from our filter. So let me hide the gain window, and now let's look at the phase, because that's what is important, as we saw for the all-pass filter. Now I'm sweeping from 20 Hz to 20 kHz, effectively the system bandwidth, but of course the all-pass filter starts at 0 Hz, so effectively DC. So already at 20 Hz, if we go to the far left of the scale, our phase is already shifted by about -2 degrees. And as we increase in frequency, we're getting this characteristic first-order all-pass filter response, where as we increase in frequency, our phase delay gets greater and greater and greater, tending towards -180 at high frequencies. Now, with our cutoff frequency set, as we just saw at 1 kHz, we should expect our phase delay, or phase, to be -90 degrees at that cutoff frequency. I can change the marker to go to -90 degrees, and that gives us exactly 1.022 kilohertz at -90 degrees. And if we look at our current setting, that's exactly at 1.022 kilohertz. So our filter is performing as it should. At low frequencies, close to DC, we're at 0 degrees of phase shift. Cutoff frequency, we're at -90 degrees of phase shift, and at high frequencies, we tend to -180 degrees of phase shift. If I adjust my potentiometer, let's say just over 3 kilohertz, and I do another measurement, the phase response will change again, and would have our -90 degree crossing at 3 kilohertz instead. So still a similar characteristic response in the phase, but if we jump to -90 degrees now with the cursor, we are now at just over 3 kilohertz as expected. So this is how we can change the all-pass filter coefficients on the fly and change the phase delays on the fly as well. Just to confirm, if we look at trace 1, the magnitude again is flat. Keep in mind the scale on the y-axis, so we're at 0 dB, the gain doesn't change. We can also look at group delay. If we change trace 2 from phase to TG, so group delay, we can also measure the group delay characteristics of our filter, which can be important in certain cases as well. Before we move over to the second order all-pass filter, let me just save this measurement, and I've adjusted the cutoff frequency to be around 1 kHz now. I'm going to save this measurement so we can compare. And now let's adjust the code to run the second order all-pass filter. For the second order all-pass filter in int main, all we have to do is initialize the all-pass filter as before, but now we have to call the second order function, which provides the cutoff frequency in hertz as before, the sampling frequency in hertz as before of the system. But now, because this is a second order all-pass filter, we also have another parameter to play with, which is the bandwidth at and around the cutoff frequency. So I've taken another variable and I've mapped that to another one of the potentiometer controls that we can play with this, but the rest is pretty much the same. The update calls are still the same as before. So now let's run that and upload that to the board. I've set my cutoff frequency at around 1 kHz as before with one potentiometer. With the other potentiometer, I've set the bandwidth to be around half that, so 500 Hz. Moving back to the Bode Analyzer suite, we've saved our first order measurement of the all-pass with a cutoff frequency of 1 kHz. Now let's perform one more measurement. So I'll click on single, and we can see how the phase response differs. And of course, we'll double check as well that the magnitude is also at 0 dB throughout. Now, having measured the second order all-pass filter with the same cutoff frequency as our first order all-pass filter at 1 kHz, but with a bandwidth of 500 Hz, we can see the blue phase trace is quite different to what we had for the first order system. The second order all-pass filter in blue also starts at 0 degrees of phase shift close to DC, and as we approach the cutoff frequency, we have a far steeper slope, that is the rate of change of phase at and around the cutoff frequency. At the cutoff frequency itself, at 1 kHz in this case, we are now at minus 180 degrees of phase shift rather than minus 90 degrees as we saw with the first order all-pass filter. Above that cutoff frequency then, we don't also tend to minus 180 degrees of phase shift, but rather we tend to minus 360 degrees of phase shift because this is a second order filter. So at the cutoff frequency with the second order filter, we're at minus 180 degrees, but we also have the bandwidth parameter to play with. Currently this is at 500 Hz, and let's see what changes when we adjust that. I've now adjusted the bandwidth to be 250 Hz, but the same cutoff frequency, so let's start another measurement. I've saved my previous trace. And now the blue trace is our new measurement of the second order all-pass filter with a bandwidth of 250 Hz. Again, we have the same cutoff frequency at 1 kHz, where our phase shift is minus 180 degrees, but because we now have a narrower bandwidth, 250 Hz compared to 500 Hz, our slope is far steeper, and the change from 0 to minus 360 degrees happens in a shorter band. So that's how the bandwidth changes this system. Of course, we can go the other way and change this, for instance, to 2 kHz. With the bandwidth now set to 2 kHz, let's see what happens. Our new curve also goes through minus 180 degrees at 1 kHz as expected, but we have a far shallower transition band due to having a far wider bandwidth parameter set, in this case at 2 kHz. But still a similar characteristic shape with a less steep of a slope. So this is how we can influence the phase change properties of our all-pass filter. And again, for all of these, the magnitude is pretty much 0 dB as expected. We can also examine the all-pass behavior in the time domain rather than the frequency domain, and this might be a bit more intuitive what's actually happening. Right now I have a wave-gen feeding the input of my digital guitar effects pedal with a 1 kHz 500 mV peak sine wave. I'm monitoring the input with my yellow trace on channel 1, and I'm monitoring the output of the pedal at channel 2, which will be the blue trace. Right now I have true bypass. It's a simple connection from input to output, so there of course shouldn't be any phase and magnitude changes. Now I can engage the pedal by pressing a foot switch. And now the yellow trace again is my input, the blue trace is the output. This phase shift we're seeing in the slight adjustment in magnitude is the inherent phase shift because we're going through now the analog hardware going into the digital platform. We're not applying any processing, we're feeding that directly to the output and then through another analog chain after the DAC. So of course there's going to be some inherent lag and phase delay due to this digital processing system. And that's exactly what we're seeing here. But now if we engage the effect, let's see what happens. Now the effect is engaged, and what we've got is this additional phase shift compared to the effect not being engaged. The magnitude hasn't changed, we've only changed the phase shift. The amount of phase delay is dependent on the frequency domain performance we saw previously. So because I'm running at 1 kilohertz, I'm going to have a specific phase delay at that frequency. If I adjust the frequency, let's say to 2 kilohertz, I'm going to have a different phase shift than before. Or if I adjust the frequency down to 500 hertz, that's going to be a different phase shift as well. And you can imagine your signal that goes into your guitar effects pedal is of course a sum of these different sinusoidal frequencies, so there's going to be a different phase shift for all of those frequencies. Now, of course, because we made this all-pass filter variable, this is currently running the first order all-pass filter, we can also adjust the cutoff frequency of our all-pass filter. So I've got this all the way down to around 500 hertz. This is a 1 kilohertz sine wave going in. And as I increase the cutoff frequency, we can see the amplitude doesn't change, but the phase shift does change. So the blue trace relative to the yellow trace is changing in phase shift as well. So exactly what we expected. We are not changing any amplitude. We're just shifting the phase depending on what input signal frequency we have. We get different amounts of phase shift, and we can adjust that on the fly using our set coefficient function. Thank you very much for watching this video. I hope it was useful, and I hope it showed you how you can implement your own adjustable all-pass filters in real time in C running on a microcontroller of your choice. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest hardware design, PCB design, embedded systems, and DSP videos. Thanks again for watching, and I hope to see you in the next video. Bye-bye.